Okay, so let's go work on another example of angular momentum. Now, I was going to do rotating baton, but I don't have baton at home. I have a small dumbbell like this. So I'm going to imagine that I'm going to rotate about an axis. So they will twirl like that. So they will twirl like that. So this will go in its own circle, and this will go in its own circle. And I want to figure out what is the angular momentum of that. So we have one mass here, and we have another mass over here. Okay? And we can say I'm going to rotate about that axis. So I'm going to rotate about this axis. So if I look at it, I'm going to also assume that the joining part, which is pretty, it's not really no mass here, but I'm going to assume this part has much less mass compared to these guys, and so I can just ignore the angular momentum of the motion of these parts. Each part will go in a circle, but I'll just ignore that. Okay, that's just a simplification. So ignoring this, so later on we can do more complete calculation, but right now I'm going to ignore that, and this one is going in this little circle. Let's call this M1. So you can see that when M1 goes 2 pi, in the same amount of time M2 goes 2 pi. Think about it, right? It goes full circle once. In the same amount of time, this also must go full circle once. But this circle is smaller. So this is speed much be smaller. So let's call it V2, and let's call it V1. And if I know how much is going to omega, so when this guy goes 2 pi, this guy goes 2 pi also. That will give me same omega. Different V's, but same omega. That's very important thing to notice, right? They really, as a one body, they are rotating, and so I can just label both of them with one symbol omega. So we notice that if this is R1 and this is R2, then we have a V1 is omega R1 and V2 is omega R2. Okay, so if this was some angle theta, at which this is not the angle of rotation, but angle at which these guys are when I'm rotating it. Is it I'm rotating straight like that or at a tilted? So this is some kind of tilt. Maybe use some other angle symbol for that. Maybe call it alpha for the tilt. So this is like a tilt. So depending on where I am doing, whether I am right in the middle or some other point, there will be a distance. If this distance was L1 and this distance was L2, with L1 plus L2 is the total distance, right? I would be able to figure out from the alpha and the L1 what the R1 will be. So if I look at R1, it looks like this. This is R1 and it's L1 and this is alpha. So I'm not going to work this out, but you should know that R1 should be equal to, if thing was not given as R1, but just given L1, so R1 will be L1 sine alpha here, But I will work my equations in terms of r's, not in terms of l's. All right. So if I look at angular momentum of, so angular momentum's calculations will go very similarly. We would have angular momentum of this guy plus angular momentum of this guy. Well, angular momentum of this guy is, if I look from the top, is going counterclockwise. If I look from the top, this is also going counterclockwise. So the two angular momentums. So you have L1 and L2. The direction is counterclockwise. Direction is counterclockwise. So they will add to give me the total will be add. So the L total, this means add them, right? Because they're in the same direction and they're vectors, they're going to add. And so the magnitude for the L1, this we just learned, if something is going in a circle is going to be using this kind of stuff. We learned that m1 r1 squared times omega. That's the angular momentum magnitude for this. Angular magnitude for that will be very similar, m2 r2 squared omega. I'm putting in parentheses because that's the moment of inertia. If you you don't need to put parentheses, just for the emphasis here. So when I add, these will add. So I'll get m1 r1 squared plus m2 r2 squared, and this is going to be common omega. Do you see that? Because they're the same omega, it kind of factors out, and so I got a new moment inertia. So this is the moment inertia together, right? So L total turns out to have same type of formula as L for the individual particles, is I total. Now I have to add up the moment inertia each one to get the total, but just have to multiply by omega, because the omega is the same for both of them. And so this is very important formula for us. So angular momentum of, not just for dumbbell, if I had say a bone or something, and bone was I was rotating or somehow around this thing. So bone will have its I. So if it's going with omega, so the L of the bone will simply be I of bone times omega of bone. So this is a very important formula. The difference will be I of the bone will not look like that. It will have its own formula for moment of inertia, how the moment of inertia works out. But fundamentally, you can think of bone being made up of a whole bunch of particles, and when I add up all the particles, they will give me a net formula for the bone. And we're going to work out for the bar next. So right now you can see how the moment of inertia kind of this has a fundamental formula, and then this is a way to add moment of inertia to get moment of inertia where there are more than one particles. This example illustrates two particle system, but you can think about 4 particles, 6 particle, n particle systems. So next video we'll look at how calculating moment inertia in various situations. So I stop here, and I will see you in the next video.